As devices getting smaller, many side effects has been generated. To overcome, we started strain engineering as a knob for the velocity saturation and mobility degradation, and also using high K gate dielectric in metal gate. But in nanoscale, those knobs cannot cover all the fundamental limits. So we started to make a new device structure. As I told you that there are fundamental limits, and the biggest one is that the lateral electric field between the source and drain beats the vertical electric field, which controls the channel area. It made us could not drive up the on current, but the off current. So it means that if we if we could not control the channel, we could not turn on and off the device, and also we could not activate the device as we want. One of the main reason caused this problem is punch through. So at first, to block the punch through current, we used the silicon on insulator, as known as SOI. Um, it blocks the path of the leakage current physically. So it made the subthreshold swing better, but it's still not a fundamental knob. To overcome the huge lateral electric field, we had to amplify the vertical electric field. So we started to stimulate the channel in different ways. This is the beginning of FinFET. We make the body as a sharp fin shape and cover it from different directions. Totally three directions. Then it makes the dimension affected by the vertical field, you expanded kind of. So we could control the channel easily with the gate bias. As it has been developed, the swing value of it has been idle. Because of the physically narrow fin structure, the body, the body has been fully depleted. So the ideal factor, which determines the subthreshold swing, has been super idle. But by the way, still all the structures are under the short channel effect. So determining the channel length is really critical. We have a formula to determine the value, which called the natural length, and it's proportional to the thickness of oxide and silicon, and in the same time it's inverse proportional to the oxide mobility. So to develop the smaller devices, we should reduce this natural length value, reduce it. So as we use the high K dielectric and the metal gate, not metal gate. As we use the high K dielectric, we could maximize the oxide mobility, and also we're making super thin body structure, so it makes we could lower the silicon thickness.